Okay, I think I just start. I'm going to do something a little bit different for, compared to the talk that you already heard. So I noticed that many talks are discuss the technologies and databases and for the in-memory computing from top to down. So what I'm actually trying to do is actually we try to build something from bottom up. And we know we have a lot of experts around here, which is actually experts at the top level, which is the database and application level and how to build the application that actually use the framework. So now I'm actually starting to from the bottom up. The first session is when talking about the storage media innovations is actually we're changing the view, changing the way that how software being developed. But some people actually may not agree with us. As said, we always keep the hardware as a black box, and nobody understands what's really going on there, and the software just needs taken care of at the top. Actually, with the innovation of the hardware, and we are actually need for some software developers, actually even users, know what's really going on. So break down the black box level, go down to the what's really inside. Actually, it's quite important. I know a lot of people talk about memory for the start of the keynote this morning, and show all the times, storage spaces, and going up. So we're starting from the SRAM all the way to the HDD, and something in the middle is coming up. Right? In older days, we have SRAM, DRAM, and then HDD. And then at this point, we have a DRAM. We have some persistent memory technology built to connect to the memory bus, which we call the memory. If something is not connected to the memory bus, we call it SSD or some other storage. But once it connects to the memory bus, and it's being called non-volatile memory or something like that. So that's the difference between those. So we actually also have a NAND technology which comes in a couple of years ago and starting to become popular starting last year or so. And then this year, Intel and Samsung and some other companies, Intel and Micron, talk about the 3D crosspoint, which is actually build a vertical level, which is for the different way as a NAND to do the storage. And I probably, since I'm coming from Intel, I probably talk a little bit more about the hardware side instead. I'm going to skip some of the slides because people already know that. One of the question, a very interesting question I encountered actually see the people are asked, if I put a very hot in-memory database in NAND or in 3D crosspoint, I have a really hot data which keep accessing that piece, that area of the hardware, of the storage. What will happen? Where this piece of thing will burn off? The answer is yes. So if we have a very hot database put inside the NAND or put inside the 3D crosspoint, and then certain areas which have a hot access, like 30,000 times, and that area will actually become hot and burn, right? So the device right now have a controller, so which actually try to look at all the sectors and areas to see which particular things hot and try to almost before burnout. And they will actually keep a state in the memory controller. So nowadays, operating system, some operating systems actually look at those devices and say, oh yeah, I send an error signal. Some operating systems basically does not do that. I have my daughter actually have a USB drive, and he keep on play something with Apple and then something with PC, and then keep the thumb drive can play around all over the place. And then one day he plugged into the Apple computer and said, "Hey, I have nothing show up." So Apple computer does not report anything, and then nothing. Basically, does not show any data. So she flagged down, see what's really going on. And I plug into the PC, which is Microsoft PC and Windows like 8. And it immediately shows there is some error on your drive. You need a repair, or you need to save something, and then we are going ahead to repair this. So then I say, OK, go ahead and repair. So in reality, is what they do. The NAND is actually only have a very a low flash. I think it's about 30K something array, or some even much lower. So it actually have certain piece of area which the file is keep hitting that. It can have a problem. The driver report I have a problem, but the iOS did not catch that. But Microsoft said, OK, I will need to repair. What it does, it marks that area is bad, move the data out, mark that area bad, and then say, it repaired, I'm done. So that actually the things I'm thinking about in the enterprise database or something like that, user, so if you are totally depends on the polling, so basically it does not report the things are going bad, you actually have actively poll this driver controller to see which is still healthy. That actually can be somehow is a huge burden if you build if you actually build starting to NAND and the 3D crosspoint and a flash. This could be a thing. You cannot really keep polling this entire driver to do this through the application level. So something needed to be done at the middle layer as well. So keep in mind that. 3D crosspoint have two stages. So the first stage is 3D crosspoint material coming out to be built as a SSD or connect to PCIe as a card. So that we call it SSD, 3D crosspoint SSD, or 3D crosspoint PCIe connector. And then this kind of this device, basically the flash rate, which can keep the health state, is about 30K or 50K or something like that. It's much better than NAND, but they still have some rate. And once the 3D cross move to the DRAM, we connect to the bus, we call it non-volatile DIMM, and that number will go high. But it's at the same thing, the data actually coming in much in a faster rate, and because like both moving, right? The hardware is moving and software use it quite, so it's still the same. So the project that I'm working on is also, we're going to build something in the middle layer, which basically will pull this kind of signal and report out as a user as well. So this is one of the things that I did not notice other people talk about this in this, so I want to mention that. So keep in mind the flash and the persistent memory have some weak side. If you put the entire database there, you have hot piece of data, then you have something to keep in mind. The hardware, it does not that perfect. So we keep that memory up, become vertical. So this is actually showing up over here. So I have this chart. The left, this is before, this is the current, and this is the future. So this chart is this graph is actually coming from Strata Hadoop world in March 30. So the people present this is kind of like, I think is Micron. We basically, it shows how the vertical memory hierarchy actually starting to build up, right? So starting from in older days, we only have DRAM and HDD with 1,000x, 100,000x differences on the speed. And right now, we are actually can see they are predicted the speed. So which see this is 100 nanoseconds, and this is actually very closer, 125 number nanoseconds over here. This is a connect to the memory bus, the DDR, so connect to the bus. So this can be quite a lot faster with a speed closer. But the capacity is much larger. Of course, if you use NAND or 3D crosspoint, they have the issue that I just mentioned. And also, 3D cross-point NVMe is coming up with a projected speed of 500 nanoseconds. So it's getting a lot closer to the speed of this. And also, this is currently that we already have and using it, it's ND SSDs. So do we still keep this as a black box to software? So that's a question to a lot of people that ask, should the software actually know this and then write a program directly use this? My answer is yes. We need to disclose the entire stack to the software developers and also even the end users to be aware, and they are able to directly use it. This is probably like with a centralized approach or versus distributed approach. So if someone said, oh yeah, I continue hide this as an entire black box away with end users, we are centralized because I'm the only person who knows this, and everybody else don't, and then I'm become a centralized user of this. This is not a very healthy to the developer point of view, which from my point of view. I have these slides from Ken Gilbertson from our architect. We are basically predict the trend is in current today. We are put a working set in the memory, and of course the memory has become bigger. But we are put on a working set over here, and we have a hot storage just use the SSD, like current NAND-based SSD or future 3D cross-point SSD. And then we have a large capacity like HDDs to store the data. But in future, actually in very near future, I don't even think next year. I probably think by the end of this year, more and more applications and frameworks are going to use this kind of a setup. We call it in-memory computing or in-memory working storage, and build above on the next generation NVM technologies. So this is kind of like where we're moving to from today, in-memory computing, to the very near future, we call it in-place computing. So this is kind of like a preview of what I'm going to introduce a new project. So this project was just moving into Apache Incubator in March. So of course, call for presenting is way before that. So I have not put on Mnemonic Project in the talk. But right now, Mnemonic Project is just preparing the first Apache release sometimes this week. So the idea behind this project is we need to solve Java problems, because Java is not going away. Some people will think, hey, Java is going away because there's so many problems. But Java is a very good, it's still very good and a very popular language to build application layer. So I look at what Apache Software Foundation projects is about 300 Apache projects. There are over 200 are built from Java. So that counts about 59.9%. So we roughly about 60% of the Apache projects in the entire Software Foundation are built on Java. And also in the big data area, the percentage is even higher. So if we look at the most popular big data projects, Apache projects today, we can see from Big Top to CloudStack, and CloudStack is quite old. So Cassandra and Spark and Flink and pretty much everything hot today are built on Java. So we are focused on how to make Java to use the persistent memory that coming up. So what exactly the Java problem? So the current problem is they actually have two problems. So one problem is if the Java programmer started to use some of the data, they have to deserialize the data from the storage into a Java heap or somewhere else. And after they completed it down, and they need to write something down, and they will serialize it down to the disk. So serialization, serialize and deserialize, the cost for that, some people actually have a rough estimate is about lower estimate is about 7 to 80%. Some high estimate is about 90%. There's a lot of things, and just by doing the serialization, deserialization into file system and up and down like this. And after the program completes, there's something inside the Java heap needs to be cleaned. Even the program is completely done, and there's some other threads coming in to use it, and there's a lot of garbage need to be cleaned. Also, during the serialization and deserialization, there's a lot of temporary objects being created, and then it will be inside over here, and it will be cleaned up, right? So there's basically serialization and deserialization will cost a lot of garbage collection pressure. It's not just by the data that being used. They also, for the serialization, serialize and deserialize, they actually create a lot of garbages as well. So there's a lot of cost between the collect of those garbages and then the SerDe cost is really significant. So what we're basically trying to think about is this model. We first, when the program starts, we load the data in the persistent memory or the SSD and so on and so forth. And we actually have a key value store, which stores a handler. So what a handler basically is a key, and the value is pointed to where the data is stored over here. So it's a key value store, basically tells where our data is, right? And after that, when we need certain of the data, we only load the methods and the volatile fields into the Java heap. And the rest of the data can be directly accessed via get set operations through the data structures stored inside the storage. This storage is more likely, I call it persistent storage in the means. So it can also be mapped as a HDD, but I don't think anybody will use that as a long distance calls, right? So it's the closest close by to the DRAM actually is a better way. So by doing that, we actually have much less garbages to collect. The only most thing to collect inside the Java heap is their handler, which tells where the data is, and also the volatile fields and the methods. We call it the schema area being loaded. But the real the data is stored over here and accessed via get set operation. So that's the basic idea of this model. In order for people to build their application to use this model, so we actually defined called a non-volatile Java object model at this point. So what does that mean? It actually, we use, so this is a Java annotation. So I think not very popular before Java 7, but it's getting a lot popular. People starting to know a lot of them, how to use them, use this annotation. So with this annotation, we basically define this as a durable entity or non-volatile entity or certain kind of entity you basically define by our project or user can define by the model if you use this model. So we basically have a handler to connect to the entity to define that. And then the real data fields, which is a heavy, large data structure or data fields, are stored inside the hybrid persistent memory storage. It can be battery-powered DRAM. It can be non-volatile memory somewhere, the NVMe device, or SSD connect to SerDe. It's all fine. So we can define those kind of objects which store their data fields, data objects into in here. So more information can be found from this link. This will tell you how to use the annotation to define your objects. So by doing that, we give the Java programmers an idea how they can actually define their objects, which specified middleware or framework to store their data. They prefer to store their data in persistent memory. So basically, in older days, when Java program this, they don't care or they don't even know where the data is going to be stored. But in this way, we give programmer a right to know or a right to specify where they want to store their data. They can use the original Java objects, and they handle that to JVM, to Java. And they also can specify this way. They basically tell us where they want to store their data, what kind of data or where they want to store, and how fast and how large their data want to be allocated in a certain place. So when we talk about data structure objects where to store, there are mainly two things, right? Time and size. So how many memory you want and how urgent you want it to be accessed, right? So we are trying to giving more ideas, to give more rights to the user to define, to try to pass down those two majority informations for the allocation of memory from user application level down to the middleware level. So then the people can communicate between hardware and the software, right? So the communication channel build up is actually quite important for the future software development or hardware development. In future, maybe in next 5, 10 years, we don't talk about software and hardware. It's somewhere, right? It's all everywhere. So it's basically converging between software programming and hardware programming will eventually converge into the same place. Software people is not just taking care of applications. They know what's underneath is. They know where FPGA program is. They will know how to use that GPU to optimize their graphics. So converge is coming with the hardware and software. So this is one of the pioneer projects that we think we throw into the community and see how people think about this. So this model is actually quite, give the rights to the people to specify where they want. So this model basically, this is a graph. This is how the allocation actually goes. When the program starts, we ask the OS where a large chunk of the virtual address space. We ask, say, we want this entire memory to be allocated for my use, for our use. And then we pretty much knows where is the DRAM. There we do the memory mapping. Where's the DRAM? Where's the non-volatile memory? From which address to which address? And then where's the SSD, right? So at this point, when we're starting to allocate each of this, and those are this is originally a handler which tells where the data is. We're starting to load only those first level objects, which called methods and the volatile fields, loads up in the Java heap, and the rest of the data accesses are directly coming from here, memory address space. So there's no serialization, de-serialization involves, and then is a pretty much in place load and stores, get and set operations will be used right over here. So the access handler goes down to the underneath is basically use a durable setter and durable getter to get the value to the computation. So their entire this area gets involved. There's no file involved here. There's no file system. There's data structures and the get set operations. So something can happen really fast if you want to access this in this kind of pattern without involve file descriptors. Passing file descriptors around. There's no files folding and unfolding, caching and uncaching, and then this de-serialization cost. So this is kind of like accessing ideas over here. Since this is a block diagram for the Mnemonic project, so we basically build the memory cache pool, and then non-volatile memory cache pool, and then memory clustering for some memory allocation needs. And then this is logic behind how to allocate the memory and where and how and in what kind of urgency. So this kind of, we basically provide a system memory allocator, then volatile memory allocator service, and then non-volatile allocator service. So underneath directly talk with hardware, and then this is the logic behind how they partition this memory allocation. So on the front side, we provide the memory buffer and the memory chunk. We know the memory buffer is have a boundary check, right? So the check to see the like bounds check, which is a little bit slower. And then we create a large memory chunk without boundary check, which is actually a lot faster. So this goes through Java here. This is using Java unsafe. And some of the memory allocation services through Java serialization costs can directly talk to the memory buffer. So some of the people actually ask, do we use JNI interface? Yes. We go through JNI, create a lot of, doing a lot of work until we settle down and then come back. We are not going to JNI up and down, up and down, up and down many times. So JNI, going down to the Java layer through JNI and then come back, which kill the garbage collection. So when you go JNI, the Java, basically the garbage collect will stop entire Java collection and flush out what already marked. So they do the concurrent marking and then you call the JNI, everything is flushed out. And when you go out of the JNI, the concurrent marking just restart. So at this point, some applications hit full GC right away. Because before you go in JNI, you have no idea what the state that the garbage collection is. They might just marking almost done, right? So that's the entire things about this. This actually helps people to getting used to the Mnemonic project as well. Basically looking at all those components and see how the logic goes. This is the high-level block view of this project. So we have a Mnemonic project. We provide the collections to the upper layer, right? So upper layer is Java-related big data or some other frameworks. So as this, we store the data into collections, data structures. So we support a linked list, array, map, and a set. Actually, the current linked list code is quite mature, and we are still testing the others. Arrays are actually easy. We are actually working on the map and set. The code have not checked in, but this is on the plan. So basically, if you have a fast data process needs, if your data storage needs can be fit into certain data structure we can call map or hash map, and this entire can be declined as durable objects. And this entire data structure can be stored in certain level of the non-volatile memory around here. And the access, we can build the allocator services to access those data, directly use get set operations, and use the model that we just present. So in this way, the optimization that cannot be done well at the Java layer, we can put down over here to do the optimization. So this project basically break down the barrier between Java objects and the native objects. So the code basically is actually, we have, the current is about, I think is called Java, because as this layer, we build more into this layer, we are actually, this layer probably shrunk. Probably about 80% of code currently is over taking care of Java needs. And this is about after goes through the Java and the native barrier, this area is about counting like 15% of the code written in the C, just the C. Okay, so to manipulate some memory allocation needs. This is all built on the C. And this is taking care of the Java side. So after we break down from Java to native, break the barrier, many optimizations can be done over here instead of at Java layer. For example, we have an AVX optimization, vectorization for the data to be accessed in the SerDe instructions from the hardware, right? But if you notice that vectorization in the Java is implemented in a very poor way, very difficult to use, right? And also, there are some other cache-friendly code in the JIT compiler is still having issues. So the Java layer couldn't do that, and the data partition, some of the optimization cannot be done in the Java layer, and we can actually be done in the native layer. So we should have a way to choose, have a framework, application developers can choose which way they wanted to do. So the idea is moving down is actually, at the native layer can be a lot faster than you optimize things in the Java layer. So that we support the models. We actually support volatile and the non-volatile use of non-volatile memory and non-volatile use of non-volatile memory. So the data type, we support the block, objects, and the generic. So when we say generic, because you know the Java is very good on the instantiate certain objects and build your own objects. So this is the way open for the other developers to extend this model to fit their own needs. So that's kind of like what it is. So another thing is this collection area is open for public to use as well. So if you actually have, if you have a certain type of data structure you are working on, and it's not inside this collection, we can actually build that collection over here as well to take advantage of the rest of the services. So this is very easy to plug in. You plug in your own collections and use the rest. So some of the Apache projects we are talking with, they are also starting to consider plug into their collections, build their own allocation server, and then take the rest of the logic over here. So that's the project is very open, very easy to be adopted. So this is one of the examples to what I mentioned before. So we have a search example. So basically, this is in the, we call it the traditional way. So we have stored the relation somewhere in the disk. We have stored file somewhere in the disk, right? So if we are trying to search Alice's coworker Ken and what they related, or some relationship between them, they are same employee, or Alice is Ken's boss, or something like that. What do? So we load the relationship up, deserialize it, right, into the Java heap, or some off-heap solution. A lot of people talk about that, but they cannot really avoid the file system, which you have to be, take the file, load over. This is deserialized, and then we have to load up the data, right? So if we assume Alice's data and Ken's data not in the same file, and in Alice's file have 100 other people, and the Ken's file maybe have another 100 people information. So what do? Since we have to load both files, right? Even we only need a little fraction of this file, we still need to load the entire file up. So this is a deserialize. This is deserialize them into here. Even we just need to find one person, and we load up with 100 person with her, right? But that's the things that we try to avoid. So what do we actually think about what we can do is, what if we just put the entire include relationship and the single data, entire data structure in here? We put the entire data structure in here. Then what will happen? So we just need Alice, right? So we load Alice up over here. Or even Alice's data can be over here, and the Alice's handler over here. So we know where the Alice is, and we know where Ken is. And when we need both of them, we just have both of them over here. We are load just in need. We are load just on time. We don't do we call it the lazy loading, is this way. We load as needed and do computation and set back. We get them up and set them back. The things that how we actually find out those two people, right? So we go through the data structure, because this is a data structure based. We put the entire data structure. If this is a map, and we follow the map to find them. If this is a linked list, we follow the linked list to find them, and then just load up. So we're doing this way to avoid the entire serialization and de-serialization in the entire thing. So another most interesting thing, when we look at this, how you actually to see what the most interesting thing for the next step that we can do. Here. What is this? We have all the data inside a data structure at a native level. We can do the optimization. This is another very interesting concept, right? People, do you understand? In the HDD mode, when your data in here, you do nothing with it, right? But once we have this data over here, this is not too far away from DRAM. This is not too far away from FPGA, GPU, CPU, right? At least in the Intel point of view, we have CPU here, GPU here, FPGA here. And where is this? This is not very far. So since the CPU is only used mostly 30 to 40%, and we have a side track of the GPU and the FPGAs, which can handle the bigger data operations and also for cloud computing very well, and why not we do optimization right over here at the native level. So that's the idea, is we can do much, much more with just the get set to serve a data store. We can optimize it very well. Can we do sort? Can we do sort here? The answer is yes. Can we do map reduce? It's still possible, right? It's not very difficult. So from here to here, this data structure and that data structure, can we do some certain of the operations? Because this is hot, and people keep accessing this piece and keep accessing this piece, join them all the time. Then why we not join before that? So there's a lot of operations we can do that with the FPGA and GPU's help, even with CPU's help, because CPU utilization is very low in today's, right, 30, 40%. When they're above 50%, your boss said, hey, we need to add more machine. Why? Because it's over 50%. Everybody's scared. But there's a lot more, right? So something we can use this, yeah, we do this. You want to sort, you want to search, or this is your search operation. After certain search operation, we say, oh, yeah, let's just sort it. So after we sort it, everything can be searched so easily, right? So the operation, once you break down the layer between this, you can think about how software actually can actually being done at the, I call it something combined with the software and hardware programming. It's going to happen. Software programs know this how to program the FPGA and the GPUs going down into this level. Why not, right? We're not dependent on hardware program component. They are saying, okay, software engineer and component design engineer is going to converge into the same person. This is where it goes, So something can happen right over here. We give the kind of very interesting things can happen right here instead of at this layer. Of course, the garbage is much less over here. And of course, at this place, we call it native computing. It's here. This can have a lot of advantages. Right over here, we call it, this component we are adding interface. Interface is already built up in this project, and we are doing a sorting here. And this is actually another piece of the combined software and hardware we're going to use, which if you notice Bruce over here, by other, they talk about a grid, right? Grid. So what if we are actually think about we have a distributed object graph, because everything in our view is becoming the objects and the data structures. And we can build this distributed object graph across the clusters, across the data centers at this point. And the technology behind that is RDMA. We can use RDMA to build a cooperation-based distributed object graph. Why not, right? if your organization, like Target, if you are starting to think about the moving, okay, so moving this, and then you can actually doing this instead of custom grid. So that's another very potential over here. So this is more like what we are positioning our mnemonic project. You can continue doing, basically for Spark and the database and all those. You can continue using this, use a custom build, your own build this. But if you are using mnemonic project, the things that you're doing the integration layer over here, and we will handle the rest of the needs. So that's the end of that. So we actually built the Spark usage model for this. So the Spark usage model, what we have done for Spark is we build a non-volatile RDD. Non-volatile RDD, based on our non-volatile object programming model, we leave the code, we do the @ sign non-volatile RDD, and then non-volatile RDD specifies their data, and those data is going to be stored in the persistent memory or storage. So we separate RDD. So RDD is data and the handler, and then we separate handler and data in the way that the line of, this is just only 6 lines of code, and people can code it like a few days, right? Not a month. Then we actually avoid the spill entirely. There's no spill of RDDs, right? So we go through this way to spill and to taking care of the data shuffling, and then we are using Mnemonic Project to handle the entire allocation. So the results is, this is actually where we do the double linked list. So this is how the program runs. The methods and handlers and volatile fields over here, and directly the data access is get and set from the storage media. So the results, this is a Scala code, which is from the k-means, and what we have is actually we add this the allocation before and the allocation later. The one line of code changes. And this is the key, which tells where the data is when the data loaded in the storage. And then this is the operation over here and the allocation over here. One line of differences, and actually changes the entire performance. So let's see. This is our storage. This is our storage. The persistent storage is we use a very popular, currently available, is not very expensive, $1,000, is 1.6 T. This is a small card in the SSD. So we put the data over here, and then we compare the performance. The data over here, we use the traditional way to, or traditional Spark and do the k-means, right? And then we use mnemonic, which we basically get set operation through instead of file system. So exactly apple to apple compare with data inside here. So then this is the results. So with this experiment, we basically see this is actually Spark memory partition. So we run the 0.6 and the 0.2 memory fraction setup. We pretty much see about we can speed up a 2x performance improve. We can speed up by 2x, twice as faster. We know when the sequential load data, the SSDs through OS system load file is not bad. They also do the preload. For us, we don't have this advantage of preload. We actually hit a couple of page faults because we're actually, there's no sequential. Everything is kind of like, we get this, we want this memory address, we want that memory address, and then coming up to us, right? So we do not take OS advantage or preload any data. So we load the data as needed. And this is the data loading. The data is available to use. We are 2 times faster because we don't have serialization. Right? The entire things we don't have serialization. We just use get set operations. And the rest of the computation steps, we also be able to speed up about 2x. Why? Why we speed up even here? Because we're just get set data, right? Why we actually speed up here? This is the reason. This is the reason. We are actually cut the garbage collection time in half. Okay, yeah, cut the garbage collection time in half. We reduce the 4GC in half, reduce 4GC time more than half, right? 56%. So in total, the time saving, we are about like 40% of time saving. So we are running exactly same application, same data sets on the same device, but with the remove of the serialization and we reduce the garbage collection, we'll be able to just speed up twice as a performance. So that's pretty much this entire project is about. I have to give the disclaimers, because while Mnemonic is operating within the period of where the application is processing their durable data, we guaranteed the persistency that happens as long as the mnemonic is closed gracefully. So that's a reasonable requirement. We call it persistent process. And if you close it gracefully, and we guarantee your data being flushed down safely. So that's the way our project is trying to achieve. This is a project community, dev list, source code, Jira tracking, website. We're still coming up a website. This is me, and this is my partner, also one of the main developers, so Apache.com. So any questions? I think I probably have this is still a pioneer, very new idea. Give the right to programmers. Like give the source code to open source, and this will boom. We don't want to hide anything. We just give the constructs to everyone to want to programming persistent. So basically is this. Everyone can declare their objects where they want to be stored, and it's going to have a potential. Yes? The question is what native library that being called here? Oh, operating system, we tested on Linux, and the code can be built on Mac OS, Linux and Mac OS. I have not tested anything on Windows. I don't think it's. The memory is anything from the disk, SATA card, all the way up. So from current available device to the future in next couple of months, we're going to have the 3D, maybe 3D cross-point coming out, and you can just reuse it. Yeah. Yeah, CPU is all supported. This is not just Intel CPU. We can pretty much support all the platforms as long as it's running OS. Running Linux, Linux probably the best. Mac OS maybe second, but Windows probably the last one, because there are so many restrictions on Windows. I haven't tried anything on Windows. Try to build something interesting on here. So I would really recommend people starting to join us with build up your own collections and try out and build up all allocation services. The Arrow project is actually come to us to say they want to build Arrow allocators. Oh, right over here, we help them build it. And then they can Arrow data representations, containers and everything, data structures, then come and build in. And then we take a long advantage to see how we actually move the Java operations into native operations, then we could do a lot of things much better. So that's the idea, to break down the barrier between those things. So that's, yeah, I think I'm running out of time. But just go ahead and shoot us an email on anything, then look at it. It should be very easy to remember. This is a way how to memorize things. OK, thank you, guys.